Paper of the day is DSM versus NSM, CPU performance trade-offs in block-oriented query processing. It's a 2008 paper. Paper has shown how different tuple layouts in the pipeline of a block-oriented query processor can strongly influence performance. For sequential access, DSM is the best representation, usually as long as the tuple block fits into L2 cache. DSM also wins for random access inside L1. If a sequential operator is amendable for SIMDization, this causes DSM to strongly outperform NSM, the difference sometimes even making it profitable to pull selection support to keep the data densely organized for SIMD. NSM, on the other hand, is more efficient for random access operations like hash join and aggregation into memory regions that do not fit L1. Unlike DSM, random access memory latency to NSM can be hidden using software prefetching. Finally, grouped aggregations allows SIMD calculations only in case of NSM. Coming to experiments and benchmark, paper analyzes the performance of NSM and DSM data organization schemas on database performance. They start with a series of micro benchmarks presenting the baseline performance on some basic data access and manipulation activities. Then they demonstrate how these benchmarks results are confirmed during the processing of the TPCH query 1. Paper uses TPCH benchmark for their evaluation. Coming to contributions, DSM is significantly faster in sequential scenarios thanks to simpler addressing large vector sizes fitting in the L2 cache, whereas the higher spatial locality of NSM makes it the method of choice when operators access memory areas larger than the L1 cache randomly. SIMD instructions give an advantage to DSM in all sequential operators such as project and select, whereas in aggregation only NSM allows to exploit SIMD. Therefore, ideally, a query processing engine should be able to operate on data in both formats, even allowing tuple blocks where some columns are in NSM and others are in DSM. Further micro benchmarks demonstrate that thanks to block-oriented processing, converting NSM tuples into DSM can be done with high efficiency. Now the PS score. Overall, this paper is a nice read, so it gets 9 out of 10 on readability. With 8 pages long, it scores 9 out of 10 on length. Reproducibility and repeatability will be a little challenging, so it gets 8 out of 10. Industry value and learning meter is decent, though not very high, so it gets 7 out of 10 on each. Overall PS score is 8 out of 10.